Hello friends, welcome back to my YouTube channel. In this class, I am going to discuss 3 more problems of chapter number 7 of Pknag's Engineering Thermodynamics, which are based upon the concept of entropy. Before starting, I must say one thing to all of you. Please do subscribe to this channel. Of course, like it and share it to your friends. Let's get started. So question number 7.10 is like this. Calculate the entropy change of the universe as a result of the following processes. First process is like this. A copper block of 600 gram mass and with Cp of, this is actually capital Cp, which is nothing but the heat capacity, and that Cp value is 150 joule per Kelvin. That is product of mass and specific heat, that is heat capacity. At 100 degrees Celsius is placed in a lake at 8 degrees Celsius. So the key point is that mass of copper block is 600 gram and heat capacity of copper block is 150 joule per Kelvin, and temperature of that copper block is 100 degrees Celsius, and the temperature of the lake is at 8 degrees Celsius. We have to find out the change in entropy of universe. So this is copper block. You see, this is copper block, and it is placed in a lake. So suppose this is a lake, is a body of infinite heat capacity. That means suppose this is lake. So water is there. So copper block, the mass of which is 600 gram. So mass of copper block is 600 gram. That is 0.6 kg, and the capital C of copper block is equal to product of mass and specific heat is in fact given, and it is 150 joule per Kelvin. And the temperature of copper block is 100 degrees Celsius and temperature of lake is 8 degrees Celsius. So in fact, when copper block is placed in the lake, what would be the final temperature? First of all, we must determine what would be the final equilibrium temperature. In fact, the temperature of copper block is higher than the lake, because the temperature of copper block is 100 degrees Celsius and lake temperature is 8 degrees Celsius. But what will happen here? The temperature of lake will not change because it will act as reservoir, because the heat capacity of lake will be higher. In fact, it will be infinite if you compare that with the copper block. So that's why no matter whatever heat is supplied by copper block to the lake, the temperature of the lake will remain unchanged. But the copper block eventually will attain the temperature of 8 degrees Celsius. So that means the final equilibrium temperature here will be TF will be nothing but 8 degrees Celsius. That is the temperature of the lake. Here lake will be acting as the thermal energy reservoir. So we want to calculate delta S universe. We know that delta S universe is nothing but delta S system plus delta S surrounding. And here surrounding means the lake. So delta S of copper block plus delta S of lake. And you can also consider this as an isolated system comprising of two composite subsystems. This is a composite system consisting of two systems. That is, one is copper block is one system and lake is another system. So this can be considered as a isolated system. We know that according to principle of increase of entropy, delta S universe has got to be greater than or equal to 0, and for any natural process it would be greater than 0, and for any reversible process delta S of isolated system or delta S of universe is always equal to 0. So here first we will find out delta S of copper, then delta S of lake. So delta S of copper block. Here what happens, heat is lost by copper block because the initial temperature of copper block as given in the question is 100 degrees Celsius, but the final equilibrium temperature is going to be 8 degrees Celsius. That means heat has to be lost by the copper block, and final equilibrium temperature is less than the initial temperature. So delta S is nothing but equal to integral of dq, d cut q by t, and which is nothing but, this is suppose T1, this is suppose final equilibrium temperature. This is mc dt upon t. Integration limit is from T1 to Ta, and that is equal to mc ln Tf upon T1. Of course, Tf is to be expressed in terms of Kelvin, and T1 is the initial temperature of the copper block in terms of Kelvin. Mass, product of mass and small c, that is specific heat, is already equal to C ln Tf upon T1. C, capital C is given and it is 150 joule per Kelvin. That is given in this question. 150 joule per Kelvin. Copper block का heat capacity है. Capital Cp stands for heat capacity, product of mass and specific heat. So delta S of copper block is nothing but capital C ln Tf upon T1, and that is 150 multiplied by ln. You see, T1, the initial temperature of copper is 100 degrees Celsius. So in terms of Kelvin, that will be 373. T1, capital T1 is 373. And final equilibrium temperature of copper block is 8 degrees Celsius. That is the temperature of lake. That is 8 degrees Celsius. And in terms of Kelvin, that will be 281. 273 plus 273 plus 8 is equal to 281. So this much of joule per Kelvin. This is going to be in fact negative because the entropy is decreasing here. This is equal to minus 42.48 joule per Kelvin. Entropy change of copper block. So entropy change of lake. You see, as the temperature of temperature of copper block decreases from 100 degree to 8 degree Celsius, that means some heat is lost by copper block, and that heat goes to lake. So that means the entropy of lake will increase, but temperature of lake remains constant. So as we calculate the change in entropy of reservoir, we have to keep the temperature of lake constant and just add the heat lost by copper. This is nothing but the heat lost by copper. Heat lost by copper. Because the heat lost by copper goes to the lake. So what is the heat lost by copper? Heat transferred or heat lost? Heat transferred from copper block is equal to capital C. In fact, that is mass, product of mass and specific heat, T1 minus Tf. That is equal to, in place of mc I can write capital C, that is heat capacity, into T1 minus Ta. C is given to be 150 multiplied by initial temperature is 100 degrees Celsius, 373 minus 21. This much of joule. This is the heat transferred from copper block. This is equal to 13800 joule. So if you want to calculate delta S lake, that will be, this heat will go to the lake. So plus 13,800 divided by temperature of lake is 8 degrees Celsius, and in terms of Kelvin that is 281. This is joule, this is Kelvin, and this becomes 49.11 joule per Kelvin. So delta S universe in this case will be minus 42.48 plus 49.11 joule per Kelvin. This is equal to 6.62 joule per Kelvin. So this is also equal to delta S of isolated system that comprises of two subsystems. One is lake and another is the copper block. And if in a question it had been asked to find out what is the entropy generation during the process, thus the answer would have been the same. Entropy generation is also equal to delta S of isolated system or delta S of universe. So same answer would have been there. So this is for case A. And for case B, you see, for case B, the same block at 8 degrees Celsius is dropped from a height of 100 meter into the lake. So lake is there, but the copper block is dropped from a height of 100 meter. Copper block. And lake is here. The copper block is dropped from a height of 100 meters, suppose 100 meter, and the copper block initially is temperature of copper block is 8 degrees Celsius, and the temperature of lake is also 8 degrees Celsius. So what would be the entropy change of universe? So you see, since the temperature of copper block does not change here, because the initially temperature of copper block is 8 degrees Celsius, when it is dropped here, it comes close to lake, and eventually it falls in the lake, then also the temperature is same. That is, copper block, temperature of copper block is here 8 degrees Celsius, and the lake temperature is also 8 degrees Celsius. So there would be no change in the temperature of copper block, because this is a reservoir, and final equilibrium temperature will be same as the temperature of reservoir. So its temperature will not change. If temperature will not change, then delta S of copper block will be MC ln Tf by T1. Just I did in the previous part. You see, this is also capital C ln Tf by T1. But here Tf is equal to T1 is equal to 281 Kelvin. So C ln 1, and it is nothing but equal to 0. So delta S of copper here is 0. Delta S of copper is here 0. So what would be the delta S of lake? You see, when the copper block is dropped onto the lake, its potential energy slowly but slowly, when the copper block starts falling from a height of 100 meter into the lake, here suppose copper block starts falling, its potential energy gets converted. As it falls down, its potential energy gets converted into kinetic energy, and eventually when it touches the lake, some sound wave is generated, and it causes disturbance in the lake. So that's why you may think that there is no heat coming into the picture. But so how can its entropy of lake will not change also here? Because there is no heat is transferred with this copper block, but It's not right. Here what happens, when the copper block touches the lake and falls down from a height of 100 meter, all of its potential energy gets converted into kinetic energy, and eventually when it falls down, eventually when it touches the lake, all of its energy is converted into potential energy, or kinetic energy is converted into heat energy. So that means when heat is added to lake, that means entropy of lake will definitely increase. So all of its potential energy of copper block, when it is at a height of 100 meter from the lake, whole of potential energy that this copper block possesses at a height of 100 meter above the lake gets converted into heat. And what is that heat amount? What is that amount? In fact, potential energy is mgh. So zero point 0.6 kg into 9.81 into height is 100 meter. So this is the heat added to the lake, and the temperature of lake is 8 degrees Celsius or 281 Kelvin. So this is in fact in terms of joule, and this is in fact in terms of Kelvin. This becomes 2.094 joule per Kelvin. This is the delta S of lake. But delta S of copper block is 0. Since delta S of copper block is 0, delta S of copper block, is 0, because here the temperature of copper block is 8 degrees Celsius and temperature of lake is also 8 degrees Celsius. So that's why its change in entropy would be 0. But delta S of lake here is 2.094 joule per Kelvin. That means delta S of universe in this case is 2.094 plus 0, that is 2.094 joule per Kelvin. So next case, that is here the same block, that was the case B, and third case is two such blocks at 100 degrees Celsius and 0 degrees Celsius are joined together. Two such blocks at 100 degrees Celsius and 0 degrees Celsius are joined together. So one block of mass 0.6 kg and another block of mass is also 0.6 kg. Same blocks, 0.6 kg. This one is having mass of 0.6 kg. One is at 100 degrees Celsius and another is at 0 degrees Celsius. When these two blocks come into contact with each other, then one would lose some heat and other would gain that heat. Heat lost by one block is equal to heat gained by the other block. And in fact, the final equilibrium temperature will lies in between these two temperatures. It will be greater than 0 degrees Celsius and less than 100 degrees Celsius, because the mass and the specific heat or heat capacity will remain the same for these two copper blocks. So if you apply the energy conservation principle, that is, for any system, energy conservation or energy balance principle is E in minus E out is equal to delta E. Here you see, if you take these two copper blocks as your system for analysis, then there would be no E in, no E out. So that means, because if you take these two blocks as your system for analysis, then no energy is going into this system and nor any energy is leaving this system. So the final equation would be delta E equal to 0, and delta E is nothing but, that means change in energy of this whole system, and delta Ik plus delta Ep plus delta U equal to 0. And in this case, delta Ik is 0, delta Ep is 0. So final equation is delta U 0. In this way, I can find out the equilibrium temperature, or you can use the equation that heat lost by one copper block is equal to heat gained by another copper block. So let Tf be the final equilibrium temperature. Final equilibrium temperature. So obviously this block would lose some heat to attain this Tf, because Tf will be always be less than 100 degrees Celsius and greater than 0 degrees Celsius. So this copper block would lose some heat. That means C is the product of mass and specific heat. T1 is 100 degrees Celsius, and in terms of Kelvin that will be 373 minus Tf is equal to C. The specific heat capacity would remain the same for both the cases, because the mass of both the blocks are same, and the same two blocks are made of same material, that is copper. So specific heat would remain same. So product of mass and specific heat would remain same for both the cases. So this is Tf minus 273. On equating this, I will find out 373 minus Tf is equal to Tf minus 273. That means Tf would be equal to 373 plus 273 divided by 2. That is equal to 323 Kelvin. So for first copper block, delta S1 would be MC ln Tf by T1. Initial temperature of this copper block is 100 degrees Celsius or 373 Kelvin. This is equal to 150 ln 323 by 373, and this is equal to minus 21.5978 joule per Kelvin. For second block, delta S of 2 is equal to 150, because the capital C is same for both the cases, 150 ln Tf, that is 323, and the initial temperature is 273. This will come out positive, and this is 25.2270 joule per Kelvin. And for delta S universe is equal to delta S of first copper block plus delta S of second copper block, and that is equal to minus 21.5978 plus 25.2270 is equal to 3.629 joule per Kelvin. You see, in all these cases, the change in entropy of universe is coming out always as a positive quantity, because all these processes are natural processes or irreversible processes. So delta S of universe is always greater than or equal to 0, and greater than 0 for natural processes and equal to 0 for reversible process only. So next question is like this. You see, a system maintained at constant volume is initially at temperature T1, and a heat reservoir at the lower temperature T0 is available, so that the maximum work recoverable as the system is cooled to T0 is this much, this expression. This is the maximum work possible. You see, this is the maximum work. So this is a system which is at a temperature T1. System which is at a temperature T1. And let a heat engine is operating between this system, and surrounding temperature is at T0. Surrounding temperature is at a heat reservoir, that is at a lower temperature T0. There is a heat reservoir here, but this is a finite body. This is not a infinite body of infinite heat capacity. So if we operate a heat engine between these two, this is a finite body of finite heat capacity. Suppose W is work produced, heat in supplied to this heat engine is Q1 obviously. So this will be heat rejected to this thermal energy reservoir, low temperature thermal energy reservoir will be nothing but Q1 minus W. So maximum work recoverable, because you see if it had been a reservoir, no matter whatever you may extract from this, its temperature will not decrease. But in this case, the temperature once you extract heat from this, its temperature would go down. So that means, and this engine would continue to operate as long as the moment the temperature of the system reaches T0, the engine would stop working. Had it been a reservoir, it would have worked continuously for infinite time period. But since it is a finite system, the engine would continue to work to the point when the temperature of system would decrease to T0. That is the temperature of this low temperature reservoir. So you see, we will apply the entropy balance principle or principle of increase of, no entropy balance principle. In fact, this is principle of increase of entropy. You know, delta S of universe for any process is always greater than or equal to 0. So here, delta S system is equal to product of mass and specific heat at constant volume. Suppose this is heat capacity at constant volume, Cv dt upon T, and final temperature is here T0, this is T1, and this is equal to Cv ln T0 by T1. Cv ln T0 by T1. This is delta S of system. And there are three parts. One is system, another is heat engine is there, and this is reservoir. So delta S of heat engine is always 0, because the working fluid completes a cycle and entropy is a property of system, and cyclic integral of any property is 0. So delta S of heat engine is always 0, because this is completing, heat engine completes a cyclic process. So change in property during a cycle is 0, and entropy is a property. So then delta S of this low temperature reservoir, its temperature remains constant, and this is the heat rejected to the reservoir, that is Q1 minus W. Q1 minus W divided by T0. So what is Q1? Q1 is the heat lost. Q1 is the heat lost by system when its temperature decreases from T1 to T0, and that is nothing but mCv T1 minus T0, that is Cv T1 minus T0. This is Q1. So delta S reservoir is, in fact, in place of Q1 I will write Cv T1 minus T0 minus W divided by T0. So delta S reservoir is this much, delta S system is this much. So delta S universe will be delta S system plus delta S reservoir, that is Cv ln T0 by T1, this is delta S of system, plus delta S reservoir is Cv T1 minus T0 by T0, minus W is there in the numerator part. So by entropy principle, delta S universe is always greater than or equal to 0. So I can write Cv ln T0 by T1 plus Cv T1 minus T0 minus W by T0 is greater than or equal to 0, or CV ln T0 by T1 plus CV T1 minus T0 divided by T0 minus W by T0 is greater than or equal to 0. Or I can write CV ln T0 by T1 plus CV T1 minus T0 divided by T0 is greater than equal to W by T0. Or I can write W by T0 is less than or equal to CB T1 minus T0 divided by T0 plus CB ln T0 by T1. So, or I can say W is less than or equal to T0 will be multiplied with both these terms. So T0 on being multiplied by this first term, T0 cancels out, and this becomes CB T1 minus T0 plus T0 CB ln T0 by T1. So W is less than equal to CB T1 minus T0 minus T0 CB ln T1 by T0, because you see ln T0 by T1 is same as minus ln T1 by T0. Since in the expression that we are going to find out as per the requirement of the question, in that expression ln T1 by T0 is there. So if we make ln T0 by T1, it would be equal to minus ln T1 divided by T0. So from this inequality, maximum work is CB T1 minus T0 minus T0 CB ln T1 upon T0. So this is equal to, taking CB common, T1 minus T0 minus T0 ln T1 upon T0. And this is the maximum work that can be obtained. And you see, maximum work is obtained only in case of reversible processes. So that means when all the processes that is working in this all the processes on which this system operates are reversible, then only the maximum work is obtainable. Otherwise, in any natural process or in any irreversible processes, work obtained will be less than this much. So next question is question number 7.12. If the temperature of the atmosphere is 5 degrees Celsius on a winter day, and if 1 kg of water at 90 degrees Celsius is available, how much work can be obtained? In fact, how much maximum work can be obtained? Take CB of water is this much. You see, in the 7.11 we derived the expression, and in this question we'll just put the values in that expression. The same question has been repeated here, only numerical values have been given. The expression just we obtained in the previous question would be used here. So the maximum work obtainable here is to be found out. For what are the numerical values here? T0 is 5 degrees Celsius, because the temperature of the atmosphere is given is 5 degrees Celsius, but the system is here 1 kg of water. Here the system is 1 kg of water, and this process would continue. This obtaining of work, process of obtaining of work, a process of extracting work would continue as long as the temperature of water decreases to 5 degrees Celsius, that is the temperature of atmosphere. The temperature would decrease obviously, because it is not an infinite body, it is not a reservoir. So once the temperature of water becomes 5 degrees Celsius, the engine or the process would stop working. So T0 is here 5 degrees Celsius, that is in terms of Kelvin, that is 278 Kelvin. Mass is 1 kg. T1 the temperature of the system is, that is the temperature of water, that is 90 degrees Celsius. 273 plus 90, that is 363 Kelvin. And Cv, small cv, is equal to 4.186 kilojoule per kg Kelvin. So if you want to calculate capital Cv heat capacity, this is equal to mass into small cv, that is 1 into 4.186 kilojoule per Kelvin, that is 4.186 kilojoule per Kelvin. So we were to obtain maximum work, so that is equal to, we will use that expression, that is Cb, capital Cb, T1 minus T0 minus T0 ln T1 upon T0, and this is equal to 4.186. T1 is 363 minus T0 is 278 minus 278 ln T1 is 363 divided by 278. So this is equal to 4.186, 85 minus 278 ln 363 by 278, and this is equal to 4.186, 85 minus 74.1653, this is equal to 4.186, 10.8346, that is equal to 45.354 kilojoule. So this is the amount of work that can be obtainable when the temperature of water is 90 degrees Celsius and the temperature of atmosphere is 5 degrees Celsius on a winter day. So this is the maximum work that can be obtained, and that maximum work will be obtained only when all the processes that occur in this engine are reversible. So thanks for watching.